Okay, so that brings us to machine learning. The engine, really.
Where computers learn without us telling them exactly what to do step by step.
Precisely. Arthur Samuel coined the term machine learning way back in '59. Self-teaching computers, he called them.
After an AI winter, it got more practical, more statistical in the 90s.
Yeah, focused on learning from data patterns. Early ideas were around like Turing's concepts, Samuel's checkers program that improved itself.
So supervised learning, that's the one we probably bump into most.
Probably. The key is labeled data. You give it inputs and the right outputs, it learns the mapping.
So it can predict outputs for new inputs later on.
Exactly. Two main types. Classification predicting categories like spam or not spam.
Finding the dividing line.
Right. And regression predicting continuous values, like a house price. Finding the best fit line.
And many of these algorithms came from statistics originally.
Oh, definitely. Linear regression. Roots in astronomy centuries ago. Logistic regression. Decision trees all started as statistical tools before becoming core ML algorithms. Even SVMs grew out of statistical learning theory.
Fascinating. And the uses are everywhere. Image recognition, fraud detection.
Spam filters, medical diagnosis, predicting churn, loads of applications.
Okay, then unsupervised learning. The flip side.
Yeah, this is about finding patterns in unlabeled data. No answers given. The machine finds structure based on similarity or difference.
Like finding groups.
Exactly. That's clustering grouping similar points. Think customer segmentation. K-means is a classic example.
And the other type.
Dimensionality reduction. Simplifying data by reducing features but keeping the main info. PCA is a big one here.
Where do these ideas come from?
Clustering has roots in anthropology, psychology. K-means was computationally looked at in the 50s. PCA is also an older analysis technique.
So this is good for exploring data, finding anomalies, maybe prepping data for supervised learning.
Absolutely. Customer segmentation, anomaly detection, organizing documents, visualization, often a first step.
Right. Now, deep learning. This feels like the really cutting-edge stuff.
It's a subfield of ML using these multi-layered neural networks. The core idea, mimicking the brain, is actually quite old, 40s, 50s.
But it had its own winter, then came back.
It did. Backpropagation in the 80s was huge, a way to actually train these deep nets. Then specialized types like CNNs for images, RNNs for sequences.
And LSTM solved the big problem with RNNs.
Yes, the vanishing gradient problem. Nets would forget early information. LSTMs from the mid-90s have special gates to control information flow, letting them learn long-term patterns. That was a game changer.
So how does it train? Backpropagation.
Yeah, data goes forward, error calculated, then calculus, the chain rule, sends the error signal backward to adjust all the connections, the weights to minimize that error, using optimization like gradient descent.
And CNNs use filters for images, LSTMs use gates for sequences.
Exactly. Deep learning's behind breakthroughs in image recognition, NLP, autonomous systems facial recognition, chatbots, self-driving tech.
Okay, one more pillar. Reinforcement learning. This sounds different again.
It is. Here, an agent learns by interacting with an environment. Trial and error, basically. It gets rewards or penalties.
Learning from feedback.
Right. Origins are cool, a mix of psychology, like learning from consequences, and optimal control theory from engineering. Bellman's work on decision processes.
How does it work, like mechanically?
An agent is in a state, takes an action, the environment changes, gives a reward. The goal. Find a strategy, a policy to maximize total reward over time, even if it's delayed. Algorithms like Q-learning help figure out the value of actions and states.
Perfect for games, right? Like AlphaGo.
Absolutely. Game AI, robotics, autonomous driving decisions, optimizing complex systems, even some recommendation systems, anywhere with delayed rewards.
So, pulling it all together, these pillars, math stats, the ML types, they all build on each other.
Definitely. Math gives the tools, ML uses them to predict, discover, decide, and many algorithms evolve from older ideas.
And you see this unifying theme, optimization.
Yes, that's a key insight. Whether minimizing error, refining clusters, or maximizing rewards, it's all about efficiently optimizing some complex function.
Calculus provides the direction, linear algebra handles the computation, stats defines the goal.
And optimization algorithms do the work. That's what makes the theory practical.
So understanding this history, these mechanics, it shows how abstract ideas become real-world tools. It's not static, it keeps evolving.
Which leads to a final thought, right? As data gets bigger, problems get harder. What's next?
Yeah, what new math or computing ideas will we need to push data science even further? Something for you to think about.